Alright guys, we've made it to the very last video for Unit 3 in AP Chemistry. In this video, we'll be talking about the Beer Lambert Law. Let's start off by exploring what colorimetry is. Colorimetry is a quantitative analysis we can use to find the concentration of a colored solution. You need to be familiar with the steps of this experiment. We start by taking some of our solution and putting it in a glass cube. We then shoot light of a single wavelength, meaning that it only has one color, at this solution. We filter the light into this monochromatic wave because it allows for a more precise measurement. Behind our glass cube, we have a detector, which will pick up how much light passes through our solution. The more concentrated our solution is, the more light it will absorb, and the less light that will pass through it. Thus, if we perform all these steps correctly, we can quantitatively record the concentration of our solution based on how much light our detector is detecting, which is a pretty nifty thing to do. So that summarizes our experiment in a nutshell. That's all you need to know about how it works. One thing I want to go over, in this experiment, I said that we shoot a single wavelength of radiation, or light, at our solution. And we do this to increase the accuracy of our results. However, which wavelength do we know to shoot at our solution? To answer this, we introduce an ultraviolet absorption spectra graph. These are kinda like the Beer Lambert graphs we just talked about, except instead of plotting the concentration of our solution against absorption, we plot the wavelength of our light against the absorption of our solution. So as you can see, starting with a wavelength of 125 nanometers and going all the way to 225 nanometers, we'll do a similar thing like in the last solution. We'll aim this wavelength at our solution, and the detector will tell us how much light is absorbed. As you can see, at a wavelength of around 185 nanometers, that is when our absorption peaks. This solution absorbs 185 nanometer wavelength the most. And so that's the one we would use in our Beer Lambert experiment to get the most accurate results. Back to the topic at hand now. There's an equation which goes alongside colorimetry, and it reads capital A equals epsilon times B times C. A stands for the absorbance of our solution. That's how much of this original light our solution is going to absorb. It doesn't have any units to go with it. Epsilon is our molar absorptivity constant, and it's going to depend on which solution we're using and which wavelength we're using. So this constant's going to be changing around, but this value will always be given to you, so don't worry about ever memorizing a table of it or solving for it. B is the path length of our light through the solution, and it's commonly in centimeters. That's the distance it has to travel through our solution in its container. And lastly, C is the concentration of our solution, and that's going to be in molarity. And so with this equation, we're also going to see some relationships which you need to be aware of. First of all, concentration and absorbance are proportional in a 1-to-1 ratio. If the concentration of our solution doubles, then the absorbance of our solution will also double. Additionally, you must also know that the absorbance of our solution will increase if either the molar absorptivity constant or the path length of our light increases. Again, this is in a 1-to-1 ratio. The next thing we have to talk about when it comes to the Beer Lambert Law is the graphs involved. In these graphs, we plot the concentration of our solution against its absorptivity. Doing so, you'll see that we get a linear relationship between the two. The first thing you need to be able to do with these graphs is be comfortable with interpreting their points and constructing one of their own. So just using this graph alone, if I know that the concentration of my solution is around 50 micromolar, even though I never did an experiment at this concentration, I know that my absorbance will be just shy of 0.5. That's what I mean when you have to be able to use these graphs. Like I said, you also need to be comfortable with constructing one of your own. For instance, if you were given a table consisting of concentrations and absorbances, you should be able to turn this into a graph. And then using that graph, you should be able to answer questions about the concentration of the solution to its absorbance. And the last part of this video, and the last thing you need to be able to do with these graphs, is understand why sometimes they might be wrong. The first such deviations can exist if we use too high of a concentration for a solution. In such cases, our absorbances, instead of being a nice linear relationship, will slowly tail upwards, which will give us a more curved slope than if our concentration had been a reasonable amount. Another deviation can exist if we rinse our cuvettes with water instead of solution in between trials. This will slightly dilute our solution, lowering our absorbance and giving us misleading results. If we rinse our cuvettes with water between every single trial, we're still going to get a linear relationship, but our actual answer is going to be off from what we would expect. because again, we've accidentally diluted our solution. However, if we only rinse a cuvette with water once accidentally in between trials, all of our results are going to be normal besides one of them. One of our results is going to be severely diluted and thus have a lower absorbance. And so while our graph should look normal for most of it, this one point right here is going to be an error. And if the AP exam asks you, why is there an error here? Then you're just going to say, we accidentally rinsed our cuvette with water. Also, we need to make sure that between trials, we're not changing the size of our cuvette. A smaller cuvette will reduce absorbance, whereas a larger cuvette will increase our absorbance. And this is due to the fact that our path length is on the right side of our equation. And so increasing path length will increase absorbance, and decreasing path length will decrease absorbance. So if we're changing cuvette size between trials for every single trial, we might get some very wonky data, which is all over the place, and of course, very misleading. And lastly, as with all experiments in chemistry, make sure that you're controlling variables. If we're not controlling our variables, our data will not be trustworthy. And with that being said, that's all you need to know about the Beer Lambert Law for AP Chemistry. And we're now also done with Unit 3. If any of this was confusing, I recommend rewatching parts of the video. If it's still not making sense, take a break and come back after. Thank you for watching.